All right, good afternoon, everyone. So let's get started. We'll review just a little bit about what we did last time. So we were looking at this linear model. We said that we have some targets, y, that we would like to predict from some features, x. And we said we're going to start with a very simple linear method, which is to scale x by beta 1 and shift it by beta 0. So this is known as linear regression, and in particular it's called simple linear regression when you use only one single scalar feature like we're doing now. So what this means is that also there's an approximation here. So we have that our true targets are approximately equal to this, but not exactly equal to them. So here on the right, we see we have the model part, which is just a line with an intercept of beta 0 and a slope of beta 1. And then we have our data points, which are given by these dots. And you can see the data points are not exactly on the line, so that's why this is only an approximation. However, we can turn it into an equality if we add this residual term here. And basically in the plot here, the residual would be the distance between the residual epsilon I would be the distance between yi and our prediction of yi based on xi. So that's what we have in terms of the model. And then we said that our objective, because essentially our goal now is to figure out what are the best beta 0 and beta 1. And we said, well, first we have to define some criteria of goodness. What do we mean by the best? And we said we're going to try to minimize the sum squared residuals. This is known as RSS. So the difference between our prediction and the target squared and summed over our data. And we said that this is what we're doing here is sort of an example of a generic recipe that we can use for machine learning. So that's sort of finishing one part of what we talked about. Then we sort of changed gears and we talked about different sample statistics that are going to be useful to for interpretation, but also to solve this problem of setting beta 0 and beta 1. So we talked about the sample mean, sample variance, and we also talked about the covariance, which talks about the relationship between x and y. And we also had this normalized covariance, sometimes called the correlation coefficient. And this is a quantity that's much more interpretable. It's always between 1 or minus 1, whereas this covariance is less interpretable because it scales with the size of the x and the size of the y. And the last thing we did is we came up with some alternative expressions that are sometimes useful. So I just want to clarify one thing because there was a couple questions at the end of the lecture last time. So what we did is we derived that the variance is equal to this. And then what I did is I moved this to the other side of the equation. And then that led to this implies. So this is not an equal sign. This is implying this new equality. So some people got confused by that. So, so basically, to summarize this in words, if you average the squared values of x, you get the variance plus the squared mean of x. Okay, and then we did something similar for this expression here. All right, any questions on anything from last time? Okay, so so today we're going to attack this problem of minimizing the RSS. And essentially, let's step back for a moment and consider what happens if we have a single variable function, some like x. X is just a scalar. And let's say that the function looks like this. And let's say my goal is to minimize, actually, this might be confusing. I'm going to call this beta just to be consistent. So this is f of beta versus beta. Okay, so let's say that my goal is to minimize this over beta. From the shape of the plot, we can see that that seems to be this point here. Maybe I'll call that beta hat, just some special value of beta that minimizes this. And my question to you is, what is happening at this point beta hat that's kind of special? In addition to the function reaching its lowest value, something else is happening. So let me ask this question to Raymond Zheng. Raymond here? Yeah, so do you see something in particular, some other thing that's happening to the function right over here? I'll give you a hint. What is the slope of the function right there?
0.
This is 0, right? Yeah. So that is a very important property. And in fact, that's the property we are going to use here and many other times to try to minimize the function. So in other words, if I can figure out where the derivative or the slope of that function goes to 0, then that is a hint of where the minimum is, right? Or where the minimizer is. This is the minimizer. The value is the minimum, but importantly, the slope at that minimizer is 0. Okay, so it's not exactly that simple because, let me continue this. Maybe what if the function does this? So this shows you that if I have found some other point, this one here, where the slope is 0, is that the minimum? No, right? That value is higher than this. So you could say that the slope going to 0 is a necessary condition, but it's not a sufficient condition. Okay. So, but it turns out for certain classes of functions, it is both necessary and sufficient. And it turns out that one of these situations that we will talk about in detail later is that if the function is convex and differentiable, then this 0 gradient point really is minimizing the function. So we're going to talk about convexity in Unit 6. Don't worry about it right now. But this is the overall approach. This is why we're looking for where this function has a 0 derivative. Okay, any questions on that? Okay, now our situation is a little bit more complicated because we actually have two different variables that we're trying to optimize simultaneously. We don't just have a single beta, we have a beta 0 and a beta 1. So it turns out that what we need in this case is we need to make a vector of partial derivatives and set that whole vector to 0. And that vector of partial derivatives is known as the gradient. So we need to set the gradient vector to 0. So here is the first element in the gradient vector. It's the partial derivative of RSS with respect to beta 0, and the second one is the partial derivative with respect to beta 1. Okay, we want each of those simultaneously to go to 0. So here's a couple of visualizations. So this is a mesh plot of the function, and you can see, sort of, it's a bit hidden, but the minimum point is sort of in the center of those ellipses down there. And if you would look right there and look in this direction, you would see that there's a 0 slope in this direction. And if you would look in this other direction, you would notice that the function has a 0 slope there. So simultaneously 0 slopes in both directions at that point. And that is the minimizer. Here's another visualization where we plot what's called the gradient field. So each of these little arrows shows the direction as well as the norm, the length of the gradient vector at that location. So like right here, the gradient has a certain size and it's pointed in that direction. And you can see as you get closer and closer to the center here, those arrows get shorter and shorter, which means that the gradient gets closer and closer to 0. And right here at the minimum, the gradient vector is identically 0. Okay. Another interesting observation is, so these are the equal height contours of this function. So like all these points here have the same RSS. And what's interesting about the gradient is it's always perpendicular to those contours. This sort of makes sense. If you travel along the contour, RSS is not changing at all. But if you move perpendicular to the contour, RSS is actually changing at a maximum rate. So another interpretation of the gradient is it tells you the direction and the slope of the fastest way uphill at that point. So when you're sitting right here and you want to go uphill, you go that way. Okay, so that's some interpretations of the gradient. Okay, any questions on any of this? How many of you guys have heard of the gradient before? Just curiosity. Okay, great. All, if not almost all of you. So, so what we're going to do next is we're going to derive some equations for the optimal parameters, but let me just write them down right now, and then we'll drive them next. So it turns out that the optimal beta 1 is this covariance SXY over the variance SXX. And we can also write this as this normalized correlation coefficient rho XY times SY divided by SX if we would like. And move that a little bit over. Okay, and we have for beta 0, it ends up being Y bar, the mean of Y, the mean of all our targets, minus beta 1 X bar. Okay, so our next goal is to derive those equations. So our approach, as we said, is to search for the beta 0 and beta 1 that simultaneously make this gradient vector equal to 0. So if we look at the first element in the gradient vector, that's this one. We want that to set that to 0. So let's take a look at this computation. So what we're doing is we're doing d beta 0, and now let's write the gradient, or sorry, the RSS. So that is going to be yi minus y hat, but let's write y hat explicitly in terms of the betas. So it's minus beta 0 minus beta 1 times xi. And then we're going to square that to get RSS. Okay, so the first thing, so this is what we need to do. We want to derive this. So the first thing to remember about derivatives, gradients, is that they're linear operations. So the gradient of a sum is the sum of the gradients. So what that means is we can move this gradient through the summation. So let's do that. In fact, I'm going to just rewrite it on the inside. So I'll rewrite this as sum of I d beta 0 this. Okay, and now we need to tackle this. This is a bit easier problem. There's no sum in there. So the question is, how do we do this? Does anybody remember there's kind of a key rule or technique from calculus that allows us to handle this? Chain rule, exactly. We want to use a chain rule. So the chain rule says, in this case for quadratic, that the derivative with respect to beta 0 is going to be 2 times this quantity times the derivative of this quantity with respect to beta 0. So we get 2 times that quantity times the derivative of that quantity with respect to beta 0, which you can just see is minus 1. And I'll just put that minus in front of the 2. Okay, everybody good with that? Any questions? Okay, let's do this again. The next one, so we have dd beta 1. We have the same quantity here. Okay, so let me ask one of you. Is Alec Robertson here? Nope. Okay, what about Akash Patel? Okay, great. So yeah, what would this be in the second case here?
Sum of I. Wouldn't it just be the same thing? Or, no, because
It's close, but it's not exactly the same. So notice the difference between how beta 0 and beta 1 appear inside there, right? So I agree that you're going to have certainly there's going to be a 2 here, and then this part is going to be the same. But now let's look at what is the derivative of this with respect to beta 1. So none of this matters because this doesn't depend on beta 1, right? So what's the derivative of this with respect to beta 1? Xi. Well, minus xi. Minus xi. So we're going to have a minus, and we're going to have an xi. And you know what? I actually didn't write it very clearly. This is an I. Okay, and yeah, I messed up here. This is an I. Okay, so so this is our expression, and yep, this is what we can get from the gradients. So now we need to just do a bit of simplification. It's not too bad, but you know, it's a little bit of work. Are there any questions before we move on? Everybody good with the partial derivatives? Okay, great. So so essentially, what we want to do is we want to sort of massage these expressions to get things that we have seen from the last lecture. So one thing that's a little bit unfamiliar to us is this minus 2 here. But because we have a 0 on the left side, I can multiply both sides of this equation here by minus 1 over 2n, and then that will cancel the minus 2 and actually replace it with 1 over n. So once we do that, we get this, right? And now the reason I'm doing this is because you can see that I've recovered an average type operator, and that's something familiar from the previous lecture. So now what we can do is we're essentially like doing this average to this sum of 3 terms, but that averaging is linear, so we can write that as averaging the first, which is this, averaging the second, and since that second is constant, you know, the averaging doesn't do anything, it's just minus beta 0, and then averaging the third, and that's going to give us minus beta 1 times the average of the xi's. Okay, so already things are starting to hopefully look a little bit familiar. In fact, this is what we saw last lecture. We called that y bar. That's the sample mean of yi. X bar here. And so altogether, if all I do is move this to the other side, then we get beta 0 equals y bar minus beta 1 x bar. Right? That's just from moving this to the other side. So we actually have recovered one of those two equations that we wrote on the previous page. So if you happen to know the optimal beta 1, then you can directly get the optimal beta 0 this way. We don't yet know the optimal beta 1, but that's what we'll work on next. Is everybody good with this so far? Any questions? Okay. So, so to go further, let's do the same thing to this equation 2. That's going to turn this minus 2 into 1 over n. And we get this, which is very similar, but now we have an xi here. And so we can, again, can expand the sum. So we're going to have one term that looks like that, and then another term that's like this. And here again, just using this for x bar, we get that. And finally, one more term there, where you can see there's a minus beta 1 in front, and then there's an average of xi squared. So that's what we have over here. And already you might start to notice some things that stand out. In fact, we derived some expressions for these yesterday, right? We could, if we wanted to, we could go plug those in. I'm going to take just a very slightly different approach. What we're actually going to do next is we are going to plug this expression for beta 0 into that right there. So let's say we do that. So we have the first term remaining the same, but now I'm going to have a minus x bar y bar here. And then we're going to have a minus x bar times minus beta 1 x bar. And so I'm actually going to group that inside this beta 1 expression over here. And then the last term is what we had there. Okay, so now maybe when we look at this, you can see some familiar things. Is anybody, actually, let me just go back to my attendance sheet. So let's see, is Simon Hoppa here? Yeah, so Simon, what, do you recognize what that first term there is? This guy? This is something we saw last lecture.
SXX? No, it's the covariance one.
Yeah, so this is SXY. So I guess one thing that we learned is that this alone is SXY plus the product of the sample means, and now we're subtracting the sample means from it, and then we just have SXY left. Okay, so then what about this one? Let me ask someone else. Let's see, is Victoria Smith here? Okay. So what is the second one, Victoria? Yeah, we could write it as SXX, or we could write it as SX squared. I'll just write it as SX. And so this is almost everything we need. So what I'm going to do is I'm going to, okay, we can write this, so like 0 equals SXY minus beta SXX. So you can now, or beta 1. So now you can see if I move this to the other side and then divide both sides by SXX, we find that we get beta 1 is SXY over SXX. Okay, so basically we recovered now both of the equations we saw previously for the least squares optimal regression coefficients, beta 0 and beta 1. So it was convenient to be able to just write them as these simple statistics, and also it gives us a little bit of intuition as to what's going on. Any questions on this last part? Okay, there's one more thing we can do, is we can figure out what is the minimum RSS. Let's find that value. So we start with our RSS expression, and then we plug in, for beta 0, we plug in y bar minus beta 1 x bar. So that gives us these new terms. And then, as a second step, so now that we've done that, let's expand this quadratic. So we can think of this as one term in the quadratic, another term in the quadratic, we expand it. And for the first term, we're going to get this squared, like this. There's a cross term where we get this times this summed, that gives us this. And then the last term, we get this thing squared, so that gives us this over here. Okay, so, but now when we look at this, we can see maybe some more structure here. So question is, what is this thing over here? So let's see, is Jake Chang here? All right, so do you recognize what that is, Jake? Almost, so there's a square on it, right? So it's a variance, so it's SY squared. But there's one other little thing that's missing. For this to be exactly SY squared, we need, see it? We need it to be normalized by n, 1 over n, and there's no 1 over n, so it's actually n times SY squared. Okay, what about the middle one? Let's see, is Joe Lippis here?
Yeah.
Yeah.
So it's the covariance, but the same thing since we're normalized to it.
Okay, good. And then the right one is just NS. Yeah, we can write SS squared, or in this case, maybe to be consistent with what's below, I'll write it as YY, like that. Okay, so we're almost done. So the last thing is to plug this in for beta 1, and you can see what happens there. You're going to get this thing multiplying this, so you're going to have an SXY. By the way, the SXY, SYX is symmetric. So, but anyway, you're going to get this times this. You're going to get this squared on the top, SXX on the bottom. You have a minus 2. And then over here, you're going to square that thing. So you're going to get an SXY squared on the top. On the bottom, you're going to get this squared, but then 1 of them will cancel out, so you'll just have that. And we're getting close, so now you can see that these guys are the same. So -2 plus 1 is -1. And we could do one more thing. Optionally, we could pull this out. And now you can see we have 1 minus this ratio. And does anybody notice maybe how we could simplify that? Let me ask, is Khaled Hamil here? Yeah. Does this term look familiar at all? Or what if I took the square root of that term? Would that look familiar?
Would be the sample standard deviation.
So it's the normalized, this correlation coefficient. The correlation coefficient doesn't have the square, and then it has a single x and y. So that's like the square root of this. So that is the correlation coefficient squared times SYY. Okay, so we have this nice, pretty concise expression here for the final sum squared error that we get when we do our least squares optimal prediction regression. Okay. All right, good. Any questions on this? Okay, so let's bring this back to our demo. One of the things we can do is we can try to predict miles per gallon using horsepower. And so this is the scatter plot we had for the horsepower mile per gallon pairs. And so now this is the code we would use to just execute the different things we derived in the last few slides. So we have, we can compute the mean of x, we can compute the mean of y, we can compute the variance of x, the variance of y. Here is our covariance. And then finally, these equations are quite simple, right? Beta 1 is just the covariance divided by the variance. That ends up giving the number, in this case, of about 40. And then the beta 0 is the y mean minus beta 1 x mean. And that ends up being minus 0.16. We'll talk about this other thing next, but for now, we have enough to plot our regression line, which is the orange one. And we can say visually, it looks like it's doing the right thing, right? If I wanted to put a line through there with some shift and some slope to minimize the sum squared of all these errors, that's the line that does it. Can't do any better than that line. And so finally, this is like the prediction we're doing. We're saying our approximation of mile per gallon is some shift plus some beta 1 times horsepower. And it's, maybe interesting, whatever the horsepower is, you multiply by minus 0.16 and add 40, and then that's this rough approximation. Okay, any questions on this? All right, so now one might ask the question, well, is this like a good approximation or is it not so good of approximation? Is there some way we can quantify the goodness of the approximation? And that is exactly what we're going to do next. We want to assess goodness of fit, come up with some particular way of looking at it. So there's the main way of looking at it when you look at like 99% of the literature, it's something called R squared. So let me try to describe R squared in one way. There's other ways to understand it, but again, our goal here is to judge whether our predictor is doing well or not well, to somehow quantify this, come up with a single number that says how well it's working. So the issue that we have with RSS, there's a couple issues. So let's remember what RSS looks like. So RSS is the sum over our n samples of true targets minus the predicted targets. And so what happens if I double my data set size? If I double n, what happens to RSS, roughly speaking? It doubles, right? So that's a little bit inconvenient in terms of RSS being interpretable, because like if someone says my RSS is 10, Well, you might ask, well, how big was your data set? Is that a lot or a little? So in order to make it more interpretable, it might make sense to actually divide RSS by n. So now you take out the scaling by the number of samples in your data set. Now that's not the only issue here, is that RSS, when you look at this expression, you can see it also depends on the size of y. So if you double all your y's, what's going to happen to RSS? It's going to go up by a factor of 4, right? Because you're squaring that doubling. So again, RSS is related to the size of y. In particular, it's related to the variance of y. So let's not only divide by n, number of samples, let's also divide by the variance. And now we have a new metric for how well things are working, or maybe you could say how poorly things are working, because as this gets larger, it means things are worse. That's a lot more interpretable. And this is almost r squared. It turns out that r squared is 1 minus that quantity, 1 minus RSS divided by n over sy squared. So this thing is defined or given the notation r squared. And this is the way that pretty much everyone describes how well linear regression works. So this is known as the coefficient of determination. The Wikipedia page is pretty good on this. There's a different interpretation of this, something that explains what does determination mean. But it's a bit more complicated, and I don't think it's really useful to get into all those details. So if you would like to learn more about it, you're welcome to click on that. By the way, every green link in these slides, or every green piece of text, is a link. So throughout these slides, you'll find tons and tons of links that go to further explanations and so on. Like, I don't have a textbook in particular, but I have a lot of explanations of things that sometimes people want more explanation of. So you can click on that link if you like. But let's take a look at this coefficient of determination, try to understand intuitively, how to interpret. If I tell you that the r squared is 0.1, that should be an interpretable number. So first of all, what is the highest value that you can get for r squared? Just by looking at the equation. So let me ask, is Pavan Etha here? Yeah, so what do you think is the 1? And how did you come to that conclusion? Yeah, so RSS, the smallest we can get RSS, which is a sum of non-negative quantities, the smallest we can make it is 0. And because of this minus sign, the largest we can make r squared is when this is 0, which is then 1. So that's what happens if we have perfect prediction, if we have 0 error in predicting our targets. So that's wonderful if you can do it. It doesn't ever really happen in practice, but if you're close to 1, you're doing a really good job. Now, what happens when r squared is 0? What does that mean? So when r squared is 0, it means that this value is 1. One way of making this value equal to 1 is, let's say that I ignore the xi's. So I'm going to call this trivial because I'm going to ignore the xi. So I'm not even really doing prediction. And all I'm going to do to make my estimation of the target is I'm going to set it at the mean of all the other targets I've seen. Right, so this answer is pretty trivial because it doesn't depend on xi at all. It's just a fixed number. In some sense, it's the best fixed number you can use, but it's just a fixed number. And when you do that, when you plug y bar into here, what does this equal? So this equals, what is this? What this equals, oops. This equals what if y hat I equals y bar? So let's see, is Josh Lees here? Yeah, so Josh, just plug in y bar into that expression. It should look a little bit familiar. Do you see it? So if this is y bar, this should look familiar. Do you remember the definition of variance. How is that different from variance? It's almost variance, not quite. If this is y bar, what else do we need to make this variance? So we just need a 1 over n in front. Then it would be variance. We don't have that, so really this is going to be n times SYY. Okay, so let's see what happens if RSS is n times SYY. So you plug n times SYY into here, you divide out the n, you divide out the SYY, and you have 1, right? And that's when you have 1 minus 1 equals 0. So if you ever get r squared equals 0, that means your performance is as good as a predictor that ignores the data altogether, ignores the x's. It just predicts y equals its mean. So that's a pretty bad predictor. There are cases when that is the optimal predictor because your data set, it's impossible to do any non-trivial prediction from your data set. Your data set is just totally hard. Okay, that can happen. I'll show you some pictures. But those are sort of the extremes of what you should expect from r squared. If you are doing least squares prediction, it should always be between 0 and 1, never outside that. Now, sometimes you might be writing some Python code and you check your r squared and it's negative. So what does that mean? It means there's a mistake somewhere in your code. If you're trying to do least squares estimation and you're getting a negative r squared, that's impossible. It means you're doing even worse than this. There's a mistake somewhere. Okay, so it can definitely happen. It's sort of like saying if your beta 0 and beta 1 were designed on a different data set and then you apply them to this data set, yeah, you might get a negative r squared because those coefficients are probably just really bad for this data set. So they're worse than trivial. That can happen. Okay, so those are sort of the extreme cases that we have. Any questions on the r squared? Okay, let's do one last thing. We'll be done then. So this is the expression that we derived for the least squares, the RSS minimizing values. So this is like when you plug them in, this is what you get. And now let's take a look. If we take this value of RSS and we divide by n and sy squared, so I'm dividing out by n, dividing out by sy squared, and then the result I'm subtracting from 1. That gets rid of the 1 and the minus. All that is left is rho xy squared. So this is when you use the optimal parameters. Then it's all about how hard your data set is. That will determine r squared, and in particular, it's all about this correlation coefficient. Remember, that thing lives between minus 1 and 1, so the squared value lives between 0 and 1, which is just what we expect. Okay, so we'll look at some pictures on the next slide. But are there any other questions before we do that? Okay, so I showed you, okay, let's just fill in the blanks here. So we said, so if r squared, rho squared, if rho squared is approximately equal to 1, which means things are very correlated. These are scatter plots that look like these. Then we know that the r squared is also close to 1 when we do our least squares fit, and everybody's happy. On the other hand, if our data set is just really difficult to work with, in the sense that the rho is close to 0, then rho squared is close to 0, and r squared is close to 0, and that gives us a bad fit. And on the bottom, we have some pictures of what different cases where that can happen. Okay, so we saw this last lecture. We said that these extreme values of 1 and minus 1 happen when all your scatter plot points land on a line. So that is perfect prediction. We saw one example of this infinitely difficult data set where the r squared, or the rho here is rho xy is 0, so r squared would be 0. So basically, linear regression couldn't do anything useful with this. But interestingly, there's other cases that are equally bad for linear regression. As a human, we can look at these and we can see a lot of structure in these data sets, but it turns out that that structure is not usable by any linear method. Linear methods are, they're simple. They can't really, for them, all of these are equally as bad as that. So So it's sort of interesting to see that there's many ways that you can get uncorrelated x and y, even though there is actually some interesting structure in them. It's just that they're uncorrelated. Okay, and then the final thing is to point out that there's different ways you can get rho xy equal 1. So we said that if the data is along a line of positive slope, actually the slope can be anything. All of these give you rho xy equal to 1. Similarly, if the line is on a negative slope, you always get -1. Now, if these are along a zero slope line, then it turns out when you look at the definition of rho xy, you get a 0 over 0, and it's impossible to really say what that is. So this is just undefined. So, and one last thing is that because your least squares coefficient, we said it has this expression, and because these guys are positive, whatever the sign of the coefficient is, it must match the sign of your correlation coefficient. So for all of these cases, your beta 1 would be positive. For all these cases, your beta 1 would be negative. And that's sometimes useful. Like you want to know, is there a positive or a negative trend in my data? So like this sort of makes sense. We probably all know that the bigger the engine in the car, the less efficient it is, so the worse the miles per gallon gets. And that would be an indication of like a negative correlation and a negative beta 1. And in fact, that's what we have. So that negative sign is because of this negative correlation rho xy. Okay. So, all right, so that's really all I wanted to say about rho xy and r squared. Any last questions? Okay, and now just one more slide for this unit, but I want to convince you that even though least squares or linear regression seems really simple, with a little bit of tweaking, it can actually be really powerful. So, and what I mean is, if you can do some sort of nonlinear transformation of your data so that after that transformation, your data looks linear, then linear regression actually can be a really great thing to do. So here's an example where instead of predicting miles per gallon, we're trying to predict the inverse of miles per gallon. So this is now our model. So this is very easy. We have a training data set of mile per gallon numbers. I can just invert all those yi's. I can get inverse mile per gallon numbers. And if I do that, this is my scatter plot. And when we look at this, we can see there's a really nice linear trend here. So a linear model is actually maybe almost optimal for this particular data. So in other words, what we're doing is we're doing like a y inverse hat is beta 0 plus beta 1x. So we're doing a linear model on this. And so now if I want to invert this, so y hat is 1 over beta 0 plus beta 1x. So in other words, we would, with this data, we would apply the equations we derived to figure out what are beta 0, beta 1. Once I know those beta 0, beta 1, I can invert the model and I can apply the model. And that's what we have down here. So here I'm taking this, plugging it into this now inverted model, and now I get this green curve, which you can see is not a linear curve in x. This is not a linear equation in x anymore, but it fits the data super well. Okay. And so, and all the heavy lifting for us, all the hard work, all the equations we had to derive, they still hold. It's just that we are applying it, to nonlinearly transform data, and then it works great. Okay. And in fact, when you look at things like neural networks, which are, today that's the most sophisticated models we have, almost all of them, what they do is they have all these like deep networks. They have all these processing layers at the beginning. And essentially all those layers, until the last one, all those layers do some nonlinear transformations, and the last layer is a linear layer. So in some sense, deep networks are doing this. They're coming up with fancy ways to transform the data, and then they're applying a linear model on that transformed data. So linear modeling, even though it seems simple, is actually super useful. It's sort of the basis for everything we do in a lot of machine learning. Okay, so that's why we're spending time on it. Okay, great. Any last questions before we move on? All right, so let's move on. We have a little bit of time left. We can start the next unit, which is on multiple linear regression. This unit is very, very similar in spirit to what we did in Unit 1. So let's see. In this case, the demo, the data set that is motivating the examples we're using is about diabetes, and it's about predicting the progression of diabetes from biometrics like age, sex, body mass index, blood pressure, and various things you get in a blood test. So we're going to use a famous data set called the diabetes data set. It's famous in the sense that it's nice and small, and it shows up in a lot of machine learning textbooks. So it has 442 different samples, and each sample has 10 predictive values, or what I call features. Here you can see they're calling them attributes, but features is what I usually call them. And this is what they are. So you have age in years, sex, body mass index, average blood pressure, and a bunch of different things you can get in a blood test. And then what you're trying to predict for this data set is some quantitative measure of how the disease progressed 1 year after those measurements were taken. So that's what we're trying, that's our target. Okay, so what we're going to do is we're going to leverage the scikit-learn package. I think I mentioned this last time, but this is the main package for basic machine learning in Python. And one of the other things it has is it has some of the more popular data sets built in. So we can actually get the data set just directly from scikit-learn. So we have to, when we import scikit-learn, we also import the data sets sub-package, and then we can just do load diabetes, which gives us a structure where we can pull out the data and the target. Here it's going to be a matrix X and a vector Y. Let's take a look at this. So these are NumPy. NumPy is what we said is our kind of numerical linear algebra, numerical just processing for Python. And when you have a vector or a matrix or something, you want to know its dimensions in NumPy, you do dot shape. So this object, it contains values, but it also has functions attached to it. So if you do x dot shape, it prints out, or here it loads into these numbers, the number of rows and the number of columns. And so the number of rows is the number of samples, 442, and the number of columns is 10, which are the number of attributes or features. Okay, so essentially we're starting to work with matrices and vectors. So let's take a closer look at this. So, so here we have a feature matrix X, which contains all the data for our features in our data set. We have a target vector Y, which contains the targets we're trying to predict. So as I mentioned, for me, I'm always going to have vectors defined as column vectors and using lowercase bold font. So here is Y. You can see it's lowercase bold, and it is a column vector. And this contains the targets, and as always, there's n targets in our data set, so this is an n-length column vector. Okay, now the feature matrix is a little bit more complicated because we have more than one feature in this case. In the last unit, we would have had just a single feature, so this could have been a vector. But now we have d different features. So for this example, we would have 10. And we, of course, have many samples. So when we load things into this matrix, we have many combinations of the feature for a particular sample and the value of a particular feature for a particular sample. That's what this Xij quantity would be. Is that making sense? So this was also, I think we saw an example in the last unit with the automobile. We saw sort of a visual example of this in Pandas because although we were only using one feature at a time, the data set actually had a number of different features. Now, for us, in terms of looking inside this matrix, it makes most sense to think about the rows as some sort of units. So for the first sample, these are my feature values. For the second sample, the next row is. So what I want to do now is I want to define a vector x, which is a column vector, but if I transpose it so that it becomes a row vector, that should be the ith row of my data matrix. Okay, so in other words, xi transpose contains the featured data for the ith sample, and it lives in the ith row of that matrix. So here you can see on the right, I'm stacking these rows on top of each other to make the matrix. First row, last row, all the rows in between. So when we look at inside this row, we see the D different features, but they're all for the ith sample in our data set. So when we talk about our data set, we can think about pairs, xy pairs, but now xi is a vector. So that's the units we're working with. Okay, is this making sense? Hopefully with some of the linear algebra review, it's jogged your memory about some of this stuff. So essentially what we want to do next is we want to do our linear model, but we want to use multiple variables, not just a single x. Now we have a whole bunch, in particular D different values for x, D different features. Okay, so how do you think we can write this as a linear model by extending what we did before? So let me ask, and it was Drake Schaefer here? No? What about Michael Otterman?
Yeah.
Okay. So do you have a guess of how we can write this with the slope and intercept type stuff? So the difference is rather than having a single x, we actually have D different x's.
So you're going to have a matrix of slopes and a matrix of intercepts? Or a vector rather?
So we're just going to focus on so our target, we're not really thinking about our data now. We're just thinking about, I have this target. It's like diabetes, Y. And I have things like body mass, blood pressure. So we don't necessarily need to think about matrices. So we're just trying to simplify it. So these are just, the xi's are just different features, different things we're trying to predict Y with. So how many intercepts do I need now?
Well, you need one for each attribute.
If I did that, if I had different intercepts, they would just be added together. So it's just redundant, kind of, right? Maybe I just need one. So let's say I have one single intercept. Call it beta 0 like before. But I do need more than one slope. So how do you think I would get the slopes involved? So beta 1 would be, let's say, one slope. How would I use that?
So you multiply that times the
Yeah, exactly. Times what?
multiply the slope times the data, right?
Yes, so in this case,
For x would be beta 1 times x1, beta 2 plus x.
exactly. Beta 1 will be our slope for x1, but we will have a different slope for x2, possibly different slope, and so on. So now I'm going to have D different slopes, but I can get away with having a single intercept. Okay, so this is the model, the extension of what we had before. As before, this is an approximation because we're not saying that Y is really exactly this, it's just close to this. And so the difference now is there's D plus 1 learnable coefficients, not just 2. So it depends, D is the number of different features we have. And we could, just like before, we could stack all the betas into a vector boldface beta. And our question then is, how do we design that vector of coefficients? Okay, last slide for today. So how can I write this y hat I? So now I've brought in the sample index I. This is the prediction of yi. Now notice I have eyes on all my data too. So how can I write that using vector notation that involves the beta vector and maybe a new vector that has the xi's? Does anybody see how we can, we have a row vector times a column vector here. Perhaps I can put in the column vector my betas, beta 0, beta 1, dot, 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 beta d. And what do I now need here to make this work? So what's the first thing I need in that row vector? See, is Brandon Young here? Yeah. Do you see what do I need to put right here so that when I multiply this by this, I get this? The number 1, exactly. What's the next thing that needs to go to the right of 1?
X1 or XI1.
xi1, right. Dot, 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 all the way to xid. Okay, so so we can see that this is our beta vector. This is going to be one row of a matrix that contains everything we need. So we see here we have the data matrix, but notice that we have appended a column of 1s, sort of as a trick, to create this beta 0 from this. So beta 0 is just multiplying a 1 to get this intercept here. And the intercept is the same for all the samples, so we just have 1s all the way down that first column. And finally, so these are our predictions as a vector. We can write this as the A matrix times the beta vector, right? Because the first element is this times this. The second element is the next row times this, and so on. Finally, you get this expression. So this is the main linear model expression that we now have in this unit. And this contains our training data. Once we have figured out how to design our beta vector, and someone gives us a new piece of data we've never seen, and we don't know what the target is, we're trying to figure out what the target is to predict it, we need to do one more thing. So let's say that I have a row vector here, and I have my beta vector. So can anyone tell me, how do I create this from X and maybe something else? So this is a row vector. So what's the first element in that row vector? 1, exactly. And all the other elements are created from this X vector. And X, remember, X alone would be a column vector. That's not useful here. But if I transpose it, I get a row vector. And now the dimension of this is 1 plus D, D plus 1 long vector. That commutes with this D plus 1 long beta vector. Okay, so this is what we do when we train our model, when we learn the coefficients. Once we've learned them, we want to implement that model. In the wild, we would use this on a new piece of data X. We'd get a new prediction. And we would have no idea how well it's working because we don't know what the real Y is, but this would be our guess. Okay, so that is a good place to stop for today. If you guys have any questions, I have a little bit of time today, but not as much. And I hope you guys have a great long weekend, and I'll see you guys on Wednesday.